talk about the naive Bayes, that is very important classifier. But you can think that the naive Bayes is we applied the Bayes theorem. I hope that you can still remember what is the Bayes theorem. The idea of the Bayes theorem is we have two events. For example, we have two events like this. This is a probability of A given we already know that B is true. For the Bayes theorem, it will be the probability of B given A times probability of A and divided by the probability of B. This is the very, very well-known theorem. So we will apply this to our classification idea. You can think that if we know some data, already known that some data, the given data is true, we would like to know the probability of some hypothesis to be true. So if you apply the Bayes theorem, it will be the probability of the data given h times pop of h divided by pop of b. So it is simple, right? And now we will try to find a maximum posterior hypothesis. What is this? The idea of a maximum posterior hypothesis, or we call it the H map, according to the books, the machine learning book of Professor Tom Mitchell. That is very well known one also. What is this? In the case that you know the given data, we have to decide when you know the probability of the data is given, you have to know that which one is higher, pop of h or pop of not h given d. Which one is higher? So of course, for example, if you know that the grass is wet, or we'll use W, is the grass or the floor is wet, and W is it's rain. Okay, so now if we know, of course, you know that we have the rules, right? If we have the rule that if it's rain, the grass or the floor will be wet, right? Okay, so when you know that it's rain, if this is if then else, so if it's rain, of course the grass will be wet. But in the real world, maybe this is a probability of the grass will be wet given it's rain. Maybe it is like 0.95, because sometimes the rain is like slight rain, and it doesn't cause the grass to be wet. Okay, so maybe it's 0.95, and when you go out and you see that the grass is wet, can you make the conclusion that it's rain? Of course, it's not, right? Maybe someone use the sprinkler, or any other reason that can make the floor wet, right? So we have to think about this. We have to think about this. When you know that the grass is wet, is it rain or not rain? So you have to find which one has the maximum posterior hypothesis. So this is rain given wet, and it is, of course, this is wet given rain times pop of rain divided by pop of wet. Comparing to pop of not rain given wet is pop of wet given not rain times pop of not rain divided by pop of wet. And if you compare these probability together, we don't need to know these values because it's equal, right? And we have to compare just only two parts here. So it is, you have to know this one, pop of wet given rain, that we already know, right? And we have to know that pop of wet given not rain. In the case of not rain, what is the probability of the grass not it will be wet? So in some case it should be like 0.2. This is just an example. And pop of rain and pop of not rain. For example, if this is the rainy season, if in the rainy season the probability of raining, it should be maybe like 0.7, and not rain, of course, is 1 minus 0.7, that is 0.3. So now we can use the values here. 0.95 times pop of rain, that is 0.7. And this one is pop of wet given not rain, that is 0.2 times by 0.3. So this is quite simple. That this one is 0.06. And how about this one? This one is 0.665. So this one is much higher. So we can conclude that this one has higher probability than this one. So you can make the conclusion that if you know that glass is wet, it, of course, the reason is it's rain. It's higher, much higher than it's not rain. Okay, so in this case, someone tried to normalize it also, because they want it to be like the summation of this one should be 1. So it can be something like this. It is 0.665 divided by 0.665 plus 0.06, while this one is probability of not rain given wet. It is 0.06 and divided by 0.665 plus 0.06. So this one will be sum up to be 1. So this is the probability of rain, and this is the probability of not rain in the case that you already know that the grass is wet. So we can apply to many cases, and I'll show you later some other example or some very well known example from the book of Professor Tom Mitchell.